A standard solid-state microchip is an incredibly powerful brain, capable of calculating billions of data points every second, but it remains physically isolated. A traditional chip cannot naturally touch, move, or feel the world around it. To interact with our environment, these electronic brains require a physical body. Microelectromechanical systems, or MEMS, bridge this gap. These are microscopic machines, ranging from 1 micrometer to 1 millimeter, designed to physically respond to the world. To deploy a car's airbag, a microscopic physical structure inside a MEMS sensor must move upon impact, triggering the life-saving mechanism in milliseconds. This diagram shows the sequence of how a MEMS device functions. It starts with a micro-sensing element detecting a physical input, like motion or pressure. That change hits a transduction unit, which processes the physical movement and converts it into a readable electrical output signal. Standard microchips are printed in flat, perfectly sealed, two-dimensional layers. But a machine requires three-dimensional volume and moving parts to perform work. This creates a daunting engineering challenge. We must carve delicate, kinetic 3D machinery directly out of a flat 2D silicon wafer without destroying the sensitive electronics sitting right next to it. To draw the initial blueprints for these structures, engineers borrow a baseline technique from traditional semiconductor manufacturing called photolithography. This diagram illustrates the exposure step. Ultraviolet light shines through a patterned mask, hitting a silicon substrate coated in photoresist. In a positive resist process, areas exposed to UV light weaken. When a developer washes over the wafer, exposed sections dissolve, etching microscopic channels. This schematic shows a negative resist. Here, the UV light hardens the exposed chemical. When the unexposed areas are washed away, physical pillars and raised structures remain. While photolithography successfully prints a precise chemical pattern, the result is strictly two-dimensional. It cannot, on its own, yield the kinetic, moving parts a machine requires. To create actual 3D space, engineers use bulk micromachining. This involves aggressively carving and removing material directly out of the silicon substrate. This method generates a massive amount of wasted material. Furthermore, the height of the structures is restricted by the physical thickness of the silicon wafer itself. An alternative approach is surface micromachining. Instead of carving away the substrate, layers of material are built up on top of the silicon. This diagram shows the innovation behind the surface technique. Engineers deposit sacrificial oxide films underneath structural layers. Once the build is complete, that middle layer is chemically dissolved, leaving floating polysilicon hinges and microscopic cantilevers suspended in midair. While standard etching achieves basic movement, it faces limitations. When an application requires tall, deep components, like fluid microvalves or gears, traditional surface and bulk machining cannot provide the necessary height. For deep, high aspect ratio 3D geometries, the industry turns to the most expensive manufacturing technique available, the LIGA process. LIGA requires an immense amount of energy. It relies on deep X-ray lithography, which can only be generated by stadium-sized synchrotron radiation facilities. This diagram breaks down the LIGA workflow. X-ray radiation exposes a thick layer of plastic, which is then developed into a mold. Metal is electroplated into those gaps, and when separated from the plastic, it yields perfect microgears with massive depth. To see how these complex 3D structures perform work, we can look at an electrochemical biomedical sensor. Inside this sensor, a tiny drop of blood is introduced to a specialized polyvinyl alcohol solution. Glucose from the blood reacts directly with oxygen inside that polymer. That specific chemical reaction releases elements that alter the flow of electricity across a microscopic platinum electrode. The physical change becomes a measurable electrical pulse. The high costs of stadium-sized lasers and complex etching are justified for applications where only these specific, deep geometries can translate physical reality into a digital pulse. Success in fabrication brings a new set of constraints, the brutal reality of protecting moving parts in the real world. Standard microchips are completely encased in plastic. MEMS devices, however, must remain open to the outside environment to measure it, yet somehow stay protected from physical destruction. This diagram shows an optical MEMS package. To let light reach internal micromirrors while keeping debris out, engineers design specialized casings with laser-ablated windows. Even microscopic contamination is devastating. A tiny amount of moisture can cause moving parts to stick together, a failure known as stiction. If atmospheric gases get trapped inside, they can dampen the precise resonant frequencies the machine relies on. Under stress, these devices also face delamination. The delicate, dissimilar thin film materials bonded together during fabrication can simply peel apart. This is the central conflict of MEMS design. If these fragile moving parts cannot be isolated from debris without blocking the signals they measure, the entire device becomes inoperable. Given the massive facilities required, the high costs, and the physical vulnerabilities, why push for this extreme miniaturization? The answer is monolithic integration. We can place both the mechanical sensing structure and the electronic processing brain directly onto the same silicon die. Because they are built using semiconductor batch processing, millions of these machines can be manufactured simultaneously on a single wafer, driving the cost per unit down to pennies. In medicine, this scale allows biosensors to run highly complex diagnostics in seconds, requiring only microscopic amounts of blood. These tiny machines now act as the nervous system for our infrastructure, sitting quietly inside our phones, cars, and hospitals. By integrating physical mechanics and digital processing in the same microscopic space, we have given computers the sensory organs required to touch, feel, and manipulate the physical universe.